Hi, my name is Max Kuttner, and this is Quantum Computing and Cybersecurity. So before going into their relationship, it's first important to define what quantum computers are and how they work. Put simply, they are just a mode of computing that operates via quantum mechanical phenomena, which may sound like a bunch of mumbo-jumbo, but basically all it means is that the mode in which quantum computers work is fundamentally different from how classical computers work, and are not intended to be a replacement for them. But if they're not supposed to replace classical computers, what are they good at doing, or what is their purpose? And quantum computers can solve problems that are intractable or too complex to solve with traditional computing, thus transcending classical time complexity. But how do they do this? Well, the principal difference between these two systems are their possible states. That is to say, bits on a classical computer are deterministic and can only be represented either as a 0 or a 1. An example of this would be a light switch. Qubits, quantum bits, however, can exist both as a 0 and a 1 as a probability, and only when observed will they collapse into a 0 or a 1 in output. And for processing power, where transistors are roughly equivalent to the power of a classical computer, qubits are related to the power of a quantum computer. And so what we just described is the first principle or behavior of quantum physics that is relative or related to quantum computers and is known as superposition, which is the ability to represent multiple states simultaneously. And this is the bread and butter that gives quantum computers an edge over classical computers. But what happens when there's more than one qubit? And this takes us to our second principle called entanglement. And all this says is that qubits are dependent on each other, which is different from a classical computer where bits are independent of each other, which is to say that the state of one bit does not affect the state of any other bits. Qubits, on the other hand, are what's known as entangled and become in one large quantum system or one large quantum state. They are connected and become dependent. What's cool about this is that the possible states can be represented as 2 to the n, where n is the number of qubits, and as few as 268 qubits describes more possible states than there are estimated atoms in the observable universe, which is pretty cool. And the final behavior utilized in quantum computers is interference, which is not unique to quantum physics, and in fact we're already quite familiar with this idea. Is just the net effect of combining two or more waves. And up until this point, we've addressed qubits or modeled them as particles. However, their movement is described by wave functions, quantum wave functions, which is the fundamental mathematical descriptor of everything in quantum mechanics. And interference can be just thought of as like a rock being thrown into a pond, the ripple or the waves that are a result of that. So that's cool, but how is it used at a quantum level? Well, when two or more bits are entangled with each other, their wave functions are added into one overall wave function. What this means is that interference at a quantum level can be used via quantum gates, which allows for the addition or subtraction of wave functions, causing constructive or deconstructive interference. And manipulation of these wavelengths alters the probability of the superposition possible states, which in turn reinforces the desired outcome or negates the undesired one. All right, that was a lot. But basically that just outlines the blueprint of quantum computing and how they work at a very high level. But what does it mean to cybersecurity? Well, what if I told you that quantum computing could break encryption and effectively the internet? And that's a heavy statement, but it is true, or it's been proven that because of the way or the most common method of securely transmitting data right now is through public key encryption, as seen in RSA or elliptic curve key exchange. And these public key schemes rely on the fact that finding prime factors for a large integer is incredibly difficult for classical computers, while finding the multiplication of two prime factors is very easy and can be done quickly. The reverse operation of that factorization is very difficult. And although for this example, 6 digits doesn't look very difficult, if that number is hundreds of digits long, it can take thousands of years, potentially thousands of years, for a normal computer to find those factors. And this is where quantum computing comes into play, as they are potentially able to find those factors in only a few minutes using what's known as Shor's algorithm, which does just that. It is able to take a large integer n and find factors, prime factors a and b, using what's known as parameter optimization, which just extracts useful information that helps lead to finding those factors a and b. And I will attempt to outline the basic steps used in this algorithm, starting with guessing a random number g that could share factors with the target number n. And taking this value g, we can multiply it by itself, and how many times we do that for it to equal some multiple m times n plus 1 is known as a value p, that power p, which is represented as g to the p equals m times n plus 1. So to find p, what we do is construct a superposition containing all the possible powers of the equation g to the x equals m times n plus 1. And when we have a superposition of all these values, a unique or interesting behavior arises from it, where in that superposition lies these frequencies where g to the x plus p is equal to some multiple m times n plus a remainder r. And we'll see that for any multiple of p, we will still get that remainder r. So we could have x plus 2p or x plus 3p and so on and so forth, but we will always have that remainder r. So what we can do with that information is just deconstructively interfere that superposition using a quantum Fourier transform to find the structural relationship or frequency 1 over p that has resulted from that remainder r. And once we have that, we can take the inverse of 1 over p to get p, and if it is even, we can plug it into this equation g to the p over 2 plus or minus 1, whose resulting value is guaranteed to share factors with n. At which point we can use Euclid's algorithm to quickly find the common factors between n and that resulting value, which in turn will be the factors we're after, a and b. At which point you can break RSA and profit from government secrets. And so, that in mind, what are the precautionary measures being taken to secure ourselves from that future where quantum computers might be able to quickly decrypt those algorithms? Well, research is being done into quantum safe or post-quantum cryptography, encryption methods to anticipate for that quantum future. And the leading researcher into that is a federal agency known as NIST, or National Institute of Standards and Technology, who are working on finalizing 4 algorithms from a 6-year standardization project. This process began in 2017 when they collected 82 quote-unquote quantum safe algorithms that were submitted for processing. And these submissions have been rigorously tested and weeded out. And just last year, they reported that roughly 15 were remaining. And so they will continue this process until, for the next 2 years, until they make their final selections. So how long are we from a quantum computing apocalypse? This is the real question, which I'm afraid to report that quantum computers currently are far below the qubit threshold required to break public key encryption. And I would say that as a technology, quantum computers are in the early stages and similar to like baby taking its first steps. And in fact, they weren't able to really be made only until the last roughly 25 years with modern technology. And another sort of parallel would be the first generation computers, such as the Harvard Mark II that Grace Hopper used and found a moth inside of, a literal bug inside of. And this kind of relates to the decoherence, what's known as decoherence of the quantum computers today, which is just outside noise of the qubits, which since they're entangled with each other, if the larger you scale the system and more qubits you have, the more susceptible it is to quantum or external noise. And as soon as one of those qubits gets a wrong output, the rest of it will collapse and fall apart. So that makes it difficult to scale, which is why it is relatively safe to say that before methods improve and become more reliable through research and microfabrication techniques, we are years, maybe decades away from quantum takeover, quote unquote, of our crypto space. And given the difficulty to make these computers, that future should not be an overnight surprise. It will instead arrive gradually, giving us time to anticipate those repercussions.